Hi everyone and welcome back. In the last class we have started liquid phase sintering and we have seen the basic driving force for this process in the last class. So we have learned that the driving force for the liquid phase sintering comes basically from a rapid transport path which is provided by the liquid once the particle surfaces are weighted by the liquid. So once that happens, once the solid particles are weighted by the liquid, it forms a liquid bridge, and through that bridge an enhanced diffusion path is provided for the densification to take place. Okay, and this diffusion is much higher compared to the grain boundary diffusion which occurs in case of solid state sintering, in the sense that the diffusion length or the thickness of the boundary across which the diffusion occurs is much larger in case of the liquid bridge compared to the grain boundary thickness in case of the solid state sintering, right? So therefore, if you see the diffusion across a grain boundary and across this liquid film or the liquid bridge that you have, because of the higher thickness of the liquid bridge compared to the grain boundary thickness, the diffusion is much higher, and therefore you get an enhanced densification in the liquid phase sintering process. Okay, so that's the advantage of having this liquid phase, and therefore this is a process of choice for sintering materials which are difficult to sinter by conventional solid state sintering. So now we will have to see the densification mechanism as to what exactly happens during the liquid phase process, and in the previous class we just started discussing this as to what happens when the liquid forms, and we had seen that when the liquid forms and it spreads over the solid surfaces, basically it creates a capillary force on the particles, and due to that the particles rearrange themselves. Okay, so that's the starting of the densification process, when the particles start to rearrange themselves because of the penetration of the liquid. Okay, so in this class we are going to continue on that and see how this densification takes place and what are the different stages of liquid phase sintering. So this slide shows you the sequence of events which occur during liquid phase sintering. So first the liquid forms as it is heated, and once the liquid forms it will flow and weight the powder particles. Initially densification occurs by rearrangement, and with continued heating the solid phase dissolves in the liquid and the amount of liquid increases until it is saturated by the solid, right? So these two things we have already seen. As we discussed, the solid should have some solubility in the liquid for this process to continue, and then the liquid phase becomes a carrier for the solid atoms, providing enhanced transport, right? Once the solid is dissolved into the liquid, it becomes a faster transport path for the atoms, and the solubility of the solid grains is inversely proportional to grain size, and therefore small grains dissolve preferentially and grain count decreases and the grain size increases, right? So when the small grains dissolve, they will actually reprecipitate on the larger grains, and this is a process known as solution reprecipitation. We are going to talk about this in more detail. And this sequence of events does not really change significantly with amount of solid or liquid. Okay, so this is how the process goes. But in order to understand the densification mechanism as to what exactly happens and how the liquid helps in the densification process, we need to first understand as to how and when does the liquid form, and how does it penetrate the solid. Okay, so let us first discuss that, and then we'll come back to this densification mechanism again with regard to the liquid phase sintering process. So consider two solid grains in contact with the liquid. Like this. These are the solid grains here, and the liquid is around it. So it has made a contact at the corners of the solid grains, and due to the surface energies, the liquid will form a groove or a neck like this with a particular angle. Okay, so this angle is known as dihedral angle. So this is an angle between the solid liquid surface energies and the solid surface energy, which is actually the grain boundary energy. Okay, so it's like this. Right, now if you take the balance of forces here, you will get this one, and from here you can see that the ratio gamma SS, that is the ratio between the solid interfacial energy and the solid liquid interfacial energy, is equal to 2 cos phi by 2. So if you take a plot between the dihedral angle and this ratio, then it will appear like this. Right, so from here you can see that when phi is equal to 0, this ratio is equal to 2, which means that when phi becomes 0, the solid-solid surface energy will just balance the solid-liquid surface energies, okay? And therefore, when this becomes greater than 2, this ratio becomes greater than 2, the liquid will penetrate the grain boundary, right? Because in this case, the two solid liquid surface energies that you have will be less than the solid surface energy or the grain boundary energy, and as a result of that, when the liquid penetrates the grain boundary, the energy of the system will decrease, okay? So that is why there is a driving force for the liquid to penetrate when this becomes greater than 2, okay? So that's how the situation is created for the liquid to penetrate the grains of the solid, and it all depends on the surface energies. On the other hand, when this ratio is small, the liquid will simply spread over the solid surface and it becomes difficult for the liquid to penetrate. Right? So only when the solid surface energy exceeds the solid liquid surface energies by more than a factor of 2, then only the liquid penetrates the grain boundaries. Right? So you need a very small dihedral angle for the liquid penetration to happen. And the scenario for different values of the dihedral angle as to how the liquid shape will be, that can be depicted through a diagram like this. This is when the dihedral angle is equal to 180 degree. The liquid will simply spread over, and as the angle is reduced, the spreading will also reduce. And the shape of the liquid will change. For example, this kind of shape is obtained for phi equal to 150 degree. This is for 120 degree. Then as you decrease it below 90 degree, then it kind of becomes like penetrating. towards the grain boundary. For example, this is for 60 degree, and then as it is decreased further down, then it starts to penetrate the solid grains, and when it becomes 0, this is when the solid liquid surface energies are just balanced by the solid surface energy. And beyond this, a complete penetration will take place when this ratio becomes more than 2. Okay. So for the liquid penetration to happen, the solid liquid surface energy has to decrease, and one of the driving forces for that is the wetting transient, which happens during the solvation process. As the solid dissolves in the liquid, the solid liquid surface energy kind of fluctuates, as you could see from here. This dashed line that you have, that shows the equilibrium value. For the solid liquid surface energy. But as the solvation happens, as the solid dissolves, this kind of fluctuates and goes below the equilibrium value, and due to that, the dihedral angle also decreases, as you can see from here. Okay. So this kind of wetting transient, as it is called, leads to a significant decrease in the solid liquid surface energy, leading to a decrease in the dihedral angle and creating the conditions for penetration. So now the other condition for this liquid penetration to happen and a better densification path to come into picture, the other condition is that the solid should be having some solubility in the liquid. Okay. So therefore we need to also see the effect of the solubility. So if you consider both the solubilities, that is the solubility of the solid and that of the liquid, good solubility for the solid leads to densification. So let us take an example to understand the effect of the solubility on the densification. So we'll take the example of two systems. One is tungsten copper and another is iron copper. Iron is soluble in copper but tungsten is not, and that is going to make a difference in the density when they are sintered by liquid phase sintering. So this one is for tungsten copper, which is having 20 volume percent of the liquid, and the upper one is for iron copper having 15 volume percent of liquid. So you can see, due to the solubility difference, although the tungsten copper system has a higher liquid fraction, the density is much higher in the iron copper system even after having a lower liquid content. This is because of the fact, as I said, iron has solubility in copper but tungsten does not have solubility in copper, and that is what is making the difference in terms of the densification of these two material systems. So the solubility of the solid in the liquid is good for densification in liquid phase sintering. However, if you have liquid solubility, that will lead to some difficulties such as swelling, which is not desirable, and therefore a high liquid solubility in the solid should be avoided. The particle radius has an effect on the solubility, and the relationship between the radius and the solubility is given by the following equation. Where S is the solubility and R is the radius of the particle, and S naught is the equilibrium solubility of the solid in the liquid. Okay, and other terms have their usual meaning, like K is the Boltzmann constant and T is the absolute temperature, and omega is the atomic volume. So this equation tells you that smaller radius particles will have higher solubility, and this is what I have already said before also, that the smaller particles have higher solubility and they will dissolve first, and this is what ultimately leads to that solution reprecipitation mechanism and the Ostwald ripening which comes into play, because these smaller particles will dissolve and the bigger ones will grow at the expense of the smaller particles, right? So that is a phenomena known as Ostwald ripening, which ultimately leads to grain coarsening in this process. Okay, and in addition to dissolution of the smaller particles, surface features like asperities will also dissolve because asperities have small radius of curvature. On the other hand, pits, crevices and necks between the particles have negative radii of curvature, and therefore their solubility is low, and hence the precipitation is enhanced in these regions. Okay, so this kind of surface features like pits, crevices and necks will act as the sites for the precipitation to take place when that solution precipitation mechanism comes into play. Alright, so before we finish this lecture, let us take a moment to summarize it. So to summarize, we can say that the solid liquid surface energies and the grain boundary energy form an angle when the liquid comes in contact with the solid grains, and this angle is known as the dihedral angle phi. Okay, and it is the value of the dihedral angle which decides the penetration. You need a small enough value for the phi for the penetration to happen, because this condition has to be satisfied for the penetration. This ratio gamma SS by gamma SL must be greater than 2 for the liquid to completely penetrate the solid. Okay. Then we have also discussed about the role of the solubility. The liquid and the solid both can have solubility. While the solid solubility is good for the densification, the liquid solubility is not good, because if you have a high solubility for the liquid, it will lead to swelling of the compact, and that is not good for the sintering process and for the integrity of the green compact. And therefore the solubility for the liquid should be minimum. Okay. On the other hand, a good solubility for the solid gives rise to a good densification by providing a faster diffusion path through the liquid bridges which form as the liquid penetrates the solid. And once the liquid penetrates, all these mechanisms will come into play. That is particle rearrangement, and then the liquid spreading through the solid and the solid particles dissolving into the liquid. And we have also seen that the solubility depends inversely with the radius of the particles, and therefore the smaller grains will have, or the smaller particles will have, higher solubility. So the small grains will dissolve and the larger ones will grow at the expense of that. Once the small grains dissolve and this mass transport happens, they will ultimately reprecipitate on the larger grains, a process known as solution reprecipitation. And surface features like the crevices and pits and necks on the surface which have low solubility will actually act as the sites for this reprecipitation to occur, and will enhance the precipitation of the solid grains. And with that, we come to the end of this lecture. But I will see you again soon for the rest of the things that we have on this particular topic. Until then, goodbye.